I think we can start now. So first of all, welcome all the participants, and I also welcome Professor Srikant Narayan, and we are very grateful that he has accepted our invitation for giving one session in this short-term course. So let me introduce his biography. So Professor Srikant Narayan received his MS Engineer and PhD all in Electrical Engineering from UCLA in 1990, 1992 and 1995 respectively, and his Bachelor of Engineering in Electrical Engineering from the College of Engineering, Gundi, Chennai, India in 1998, 1988. From 1995 to 2000, he was with AT and T Labs Research, Florham Park, and AT Bell Labs, Murray Hill, first as a senior member and later as a principal member of its technical staff. Currently, he is a university professor and holder of Nicky and Max Nikias Chair in Engineering at the University of Southern California, and a professor in the Signal and Image Processing Institute of USC's Ming Shai Electrical and Computer Engineering Department, with joint appointments as professor in computer science, linguistics, psychology, neuroscience, pediatrics, and otolaryngology, head and neck surgery. He is also the inaugural director of Ming Shai Institute and a research director for the Information Science Institute at USC. He was a research area director of the Integrated Media Systems Center and NSF Engineering Research Center at USC, and was the research principal for USC Pratt and Whitney Institute for Collaborative Engineering, a unique partnership between academia and industry between 2003 to 2007. Srikant Narayan is a fellow of National Academy of Inventors, the Acoustical Society of America, the Institute of Electrical and Electronics Engineers, the International Speech Communication Association, and the Association for Psychological Science, and the American Association for Advancement of Science, and the American Institute for Medical and Biological Engineering. So with this, I welcome Professor Srikant Narayan to take the session. So over to you, Srikant sir.
Thank you so much, Pete, and thanks to the organizers for inviting me to be a participant in this short course. I'm glad to be here. And, greetings from Los Angeles, where it is the evening time, and I think most of our participants are in India. And so, good morning to all of you there. So today, I'm just going to give you an overview talk of some of the work we've been doing using signal processing and machine intelligence on speech and sort of spoken language signals, especially for health applications. That's going to be the theme of today's presentation. It's somewhat of a reprise of a recent talk I gave at NCC. So for those of you who have listened to that, this is probably a little bit a repeat or boring, but feel free to stay and ask me questions and give me a hard time. With that, so I want to start with a broader sort of a picture of what I've been sort of calling human-centered machine intelligence, both the promise and the possibilities this domain holds. So there are exciting sort of advances that are happening, in a very convergent way along two sort of directions of interest, or themes. One in the technology front, right? Everything from advances in sensing, that is the ability to observe and measure phenomena, both people and the world in which people operate, whether it is how we interact and communicate, how we move, where we are, etc. Alongside advances in computing these days, computing at the edge and cloud, right? And everything in between is tremendous. A phone can do amazing things that was not even possible 2 years ago. With advances in algorithmic areas, notably, I'm just using the umbrella term machine learning, right? But underlying that are various things that are essential in signal processing, information theory, statistics, and optimization, and so on, have come together to make algorithms, do amazing things at scale. And of course, data communication, the ability to share data between people and between devices and so on. And of course, finally, the sort of the interfaces, that is the connection between people and with technology, right? So, and then the interesting thing is the convergent advances that is alongside everything coming together to enable amazing possibilities that that were not possible, like even sort of a few days ago, right? So it's a very interesting pace at which things are growing. The second, also sort of more from a human point of view, I feel that there's been, with this data and technology revolution, also has had an impact on democratizing aspects of research and development in many ways, right? With things like cross-disciplinary partnership. This tool represents a number of domains, right? Even though speech is at its core, I saw the diversity in the kinds of talks people have been, in many health applications with speech, with the biosignals related to speech production, but also core aspects in algorithms, right, and speech enhancement, and deep learning for speech, etc. So a whole variety of things that are happening across disciplines, but also sort of sharing of resources like data, tools, and know-how, and especially inspired by societally sort of important domains. And the domain of education and health, exemplifies as more than anything else, right? The way to understand how people learn, how people sort of, how we can understand health condition and in fact support health applications. So these two sort of themes, right, are making a lot of novel new possibilities which hold a lot of promise for understanding, supporting, and sort of and enhancing human experiences, right? And so, and that's one sort of big part that I'm going to touch upon in this particular presentation. Of course, when we say human-centered, right, that is data, everything that's about people and for people, right? So the implicit sort of requirement is that these technologies that we develop, right, whether it's algorithms or systems, should work for everyone in all contexts, right? So essentially, they have to be inclusive, right? It should work whether it's a child or a grown-up. It should work whether someone is healthy or not, whether they speak a language as a first language, as their first language or as their second language. It doesn't matter whether they're in a noisy environment or not, right? And so this has been, in fact, a big, even though it has gained a lot of extra attention lately, in various under various monikers, fairness, bias, and so on. Speech processing researchers have been thinking about this for a long time, right? In terms of robustness, in terms of enabling broad access and so on. So, and there's more to do, especially in reaching this promise, right? So with speech, right, like this human-centered technology can help us understand not only what someone is saying, but information about all sorts of things like who is it, where are they, how are they speaking, when is this happening. A lot of different pieces of information can be gleaned using machine intelligence, and speech and spoken language in this human-centered machine intelligence world plays a very key, important, central role. Right? So let's look at an example.
And then he got stung by bees to be a lion again, to be a regular lion again. Okay.
Yeah, good job.
So even in this, a short little video clip, right? You saw a parent and a child interacting, making a story together. You saw a lot of rich verbal and non-verbal behavioral cues and interaction that's going on, right? In addition to speech, you heard sort of non-speech vocalization, laughing, for example. You saw sort of, people, the co-occurrence of visual and verbal, sort of vocal verbal behavior. and so on. So there's rich sort of information that is being exchanged and reciprocity, and this back and forth sort of part of an interaction is a very sort of essential sort of a rich aspect of human speech interaction. So for us to develop technologies, right, that kind of try to understand this rich interaction, it requires us to sort of look at many different aspects or pieces of it, right, and both independently, and together. In addition, right, to what we can hear and what we can see, right, there are other things also that are sort of now happening when two people are interacting, right, like some of the bio physiological cues, such as on the insect, right, I show two little curves, right. These are basically electrodermal activity, basically of the sweat activity on a wristband sensor that each of these interacting participants were wearing, this child and the child's parent, and it kind of provides an index of the physiological arousal. And you can see this interesting pattern of alignment and and divergence that's going on. That gives you additional piece of information about this sort of auditory and visual, verbal, non-verbal behavior. So there's much to sort of gain. Some of it is sort of perceivable and interpretable by human listeners and viewers. Others maybe sort of be illuminated by machine learning algorithms. Both from the perspective of humans, but also looking at patterns that are something. Both are possible. So in general, right, taking an even higher level view, so that we can think about human-centered, behavior and interaction, right, within sort of this this complex of mind, brain, body behavior sort of connections. That is, that connects the neurocognitive system to motoric systems to actual behaviors and interactions. And for machine intelligence ecosystem to be able to understand and support this sort of complex behaviors and interaction, right, it has to involve not just machine learning, right, but first of all the ability to observe, that is sensing, the ability to analyze and process this data, that is look for things that have useful information for the questions we're trying to answer, the ability to understand and interpret basically the information that you have gathered and processed, and the ability to meaningfully respond and interact, right, either with another human or with some autonomous system or whatever. So this kind of ecosystem, this loop that's important, and together, right, makes this machine intelligence ecosystem. So that's what I was saying, with convergent sort of advances that are happening in all these domains, right, and in an integrated way, is what's creating these very encouraging possibilities in in many domains, including health. So I'm going to sort of quickly touch upon one of my favorite topics in speech science, just to give you an example of again where machine intelligence is helping us with one domain, application area, basically speech science and related clinical applications. But the bulk of my talk will focus on behavioral and mental health as sort of use cases to help us sort of highlight some of the speech processing or speech-centric machine intelligence possibilities. So just to highlight this, topic, so one of the things that has been happening is technology has always helped us understand the fundamental basic speech science, right? How we produce and process speech, right? For example, cognitive conception of speech to its execution with articulation, to actually how that translates into signal properties like acoustic signal that we measure with the microphone and how it's processed by humans, etc. Right? Of course, as we all know, right, the technology applications for this speech signal that we produce are tremendous, right? In whether it's just automatic speech recognition, biometrics, or speech synthesis, and so on. But also, there are a lot of increasingly interesting applications that are happening in the diagnostic and therapeutic area, right? And so in this domain, right, one of the things that we've been trying to see is like to peek into the very production process, the generation process, how we produce speech, and try to see how that can help us inform both scientific models of speech production, again, I will illustrate that with this converging sort of ability to sense, that is image and measure, and with machine learning, deep learning and so on, that we are able to increase or improve our understanding about the speech production models and its implication for sort of various application domains, right? And so what is the kind of data we're talking about, right? Here, what you're going to see is this video that some of you may see in this, that of a slice to a person's head as they're speaking. Let me play this and it'll become clear. So here, just to orient you, are the lips where my arrow is. The red arrow points to the tongue, and this points to the velum that opens and closes the nasal pathway.
When the sunlight strikes raindrops in the air, they act as a prism and form a rainbow.
So this was like, we've been using advances in signal processing, everything from compressive sensing to parallel imaging and, constraint reconstructions, advances that are happening in optimization and so on, to progressively improve our frame rates of MR. That is how well you can observe or image moving sort of, moving tissues actually, inside, like the tongue and the articulators. The recent, our things is over 100 frames per second, such as, this child's.
They act as a prism and form a rainbow. The rainbow is a division of white light into many beautiful colors.
So with this kind of data, right, from many people, now we can apply, right, it's rich data, like lots of data. Now we can unleash, our sort of advances in speech and audio processing alongside computer vision to start modeling, multimodally for speech science. So one particular question in this panel is I'm showing just a snapshot of 6 different individuals. You can just by looking at it, right, you can see how differently each one is, anatomically and morphologically, characterized. And so it is with this vocal instrument, everyone speaks, even they speak the same language. And so you are going to have signatures of what is sort of, common for given the sounds of the language they produce, but also what is unique to the particular speaker. Can we disassociate these kinds of things, understand what makes, speaker recognition work from the speech signal, and so on, right? These kinds of questions can be answered now, even scientifically. Of course, we can go into more applications, clinical applications. For example, I'm going to show here, I'm showing, 2 images of 2 cancer patients. What you're seeing here is in the left is a patient that had cancer in the oral, sort of the front part of the tongue, which was surgically removed. That surgery is called glossectomy, that is removal of part of the tongue, and then reconstructed with a flap, right? So we can try to see, how this will affect the speech process, or even how we can sort of understand they regain, functions like speech and swallowing. So, you can actually image and see, and, we can bring machine speech processing and machine learning ideas to actually understand, what's happening in a clinical case, from a basic first principle science point of view.
She has a backsuit and this is better out there.
So this patient actually had much of the oral part of the tongue removed, but she can still speak, and you can make out much of it. So this kind of provides us understanding about the fundamental aspects of how we sort of encode information in speech, and what happens if the speech system is sort of perturbed by disease or surgical intervention, etc. So it's exciting times. So in fact, I wanted to highlight a recent data set we just released from 75 speakers. It's freely available, and it has videos of people speaking, 2D real-time videos with audio, of course, 3D volumetric of people, and very high resolution anatomical sort of images. So this allows to apply all these sort of advances, some of these we've been, learning in this short course from various professors and lecturers to this new data set, right? And you can answer a lot of very interesting questions about, why are people like, how are people different? What is similar? What is different? How are particular sounds characterized across, people, both, the first language speakers of English and second language speakers of English here, etc. It's a fairly large data set, very unique. So I hope some of you might find it interesting. So now let me shift gear and move to the sort of main part of my talk. So, as we know, there's a global sort of need in sort of in the mental health and well-being of people, right? Across the lifespan, as we will talk about. And so what can engineering, and the kinds of things we do, especially in speech processing, be of use, right? We know that there is advances, as we pointed out, happening from sort of, the ability to sense, from, using wearable devices or devices that, like, in particular environments, like, I think someone's microphone is on. If people wouldn't mind muting if they're not speaking, that'd be great. Thank you. So as I was saying, right, so we can have, audio recorders, on person in the environment, like, we have a lot of these smart speakers that are that have the ability to sort of record audio. And as we talked about, like, advances in sort of engineering computing methods, with which, right, we are able to illuminate very, not just what someone is saying, but very nuanced aspects of human traits and mental state. Be able to sort of understand the age of a speaker or the perceived expressed sort of affect in their sort of from their voice, etc. In turn, right, these can be used to inform novel screening, diagnostics, and intervention support, especially in mental and data. So I'll use a few examples to show that. So in summary, what we're going to do is to seek a window into this hidden physical and psychological state and behaviors of people using sort of engineering approaches and technologies. Right? Why? Right, engineering, these kinds of methods, right, not only provide scalable, broadly accessible, and cost-effective ways, they also kind of provide tools for us to think about things that we haven't been able to imagine yet, right? Tools for discovery. Right? So, and why is this important? I'm showing some statistics, that I pulled out from one of our papers to just show the prevalence of some of the health conditions, right? This is just for the US, but this is not just unique to the US, right? Across the lifespan, from developmental disorder like autism spectrum disorder, which is usually diagnosed early in life, but it's a lifetime condition, and to late in, like, often, like, happen later in life, like Parkinson's disease or dementia and so on, right? So these are all, like, highly prevalent and have a tremendous sort of impact on society. So if technologies, right, especially easily sort of observable and hopefully sort of interpretable information from speech and spoken language, because it comes from a complex integration of many systems underlying it, right? From, as we said, right, connection between brain, body, and behavior are all reflected in how we speak and interact and communicate. So we can try to see if the signal bears information about these conditions or changes in these conditions. So, for example, right, in autism spectrum disorder, right, it is in the US, it's the prevalence is 1 in 54, but mainly, even though it's neurogenetic in its etiology, it's characterized by difficulties in social communication, reciprocity, that is this give and take that we have when we interact, repetitive and stereotype behaviors and interests. So clinically, right, when people try to characterize this condition and understand, right, they look for various sort of social constructs about social communication. For example, turn-taking behavior, the presence or absence of shared enjoyment, that is, people enjoying a moment together, right? Like you saw in this example, the child and parent were having, laughing together, right? And then things that are sort of, relational, like joint attention, that they're paying attention to. And maybe there are mechanisms underlying interaction that may not be these just visible or audible to us, like synchrony in behaviors that are very difficult to sort of just observe and code. So technologies can help kind of measure and model these kinds of complex aspects of interaction that may sort of shine light on this condition, to help sort of a clinician stratify behavior, understand behavior change. Another domain, right, to the other end, like is psychotherapy, right? It's it's one of the main key forms of sort of treatment for many behavioral mental health conditions, right? But still, what is elusive is understanding what works for whom, how, and why. In psychotherapy, we were sort of a trained clinician is trying to help the person using a number of different therapeutic sort of processes and so on. So here in this example, I have a particular form of psychotherapy called motivation interviewing, where a therapist helps her client to sort of seek the desired outcome that they want, right? So it involves it's talk-based therapy. So a lot of aspects of a conversation, like reflective listening, expressing empathy, are all considered to be good therapeutic sort of aspects. Likewise, right, looking for language, speech and language behavior, such as showing commitment to change and so on, are aspects that are sort of point to sort of good therapeutic outcomes. So these are some things, right? One can imagine that we can use speech and spoken language processing to understand and see characterize a particular therapy related to an outcome. For example, one of the constructs that's supposed to be a good marker of quality therapy is supposed to be the empathy expressed by the therapist, particularly from the viewpoint of an observer, like here, the patient. Right? And so let me show you that clip.
Like drinking being like this huge deal, and I don't ever really think about like how much I drink, and like filling out like how much I'm drinking every day was like, whoa, like I just didn't ever really think about it like that. I was like, if I try to actually count the drinks, it's.
So you see that the therapist is just listening, acknowledging, and so on. So these are all considered to be good. But now you can actually analyze the whole session with, some of the speech processing techniques, right? Everything from diarization to automatic speech recognition to modeling, some of the constructs. Now you can actually provide interesting insights about this. We'll come to this later. But this doesn't need to happen, in a clinical thing day to day, right? We can try to see, for example, understand, how we regulate our daily stress from how we use speech and language, or predicting things like conflictual situations before they happen. They're all possible with this kinds of, sensing and machine learning, and this integrated way of the machine intelligence, human-centered machine intelligence ecosystem, right? So we'll talk about it again, just to emphasize that the way we, at least I look at it, it's not just machine learning aspect, but looking at the full ecosystem to think about when we are trying to solve, especially problems in health and so on. So in summary, right, human-centered machine intelligence helps us to think about how we can support decision-making in health and to take the right action and response using this combination of sensing, data sciences, and AI technologies. Right? So on the one hand, these advances, algorithmic and technological advances, can help us do things that we know already how to do, what we are trying to look for. Say a clinician may be looking for specific things, but maybe it will make the process more efficient, consistent, cheaper, whatever. But it can also, as I said, right, help handle new data and create new models to offer insights, such as for discovery, right? That's why I showed you the example of this MRI data, peering into people as they speak, and to build our science. Right? Of course, these kinds of machine intelligence can also help us create tools. At the end, right, we want to help people just in the health domain by supporting novel diagnostics, new ways of doing personalized interventions, and of course tracking response to specific treatment. We will touch upon some of these examples. So how does this all work, right? So while sounds and words offer sort of, very key part of the information, right? It is often accompanied by visual information in cases, where it is possible, and they together give us a peek into the hidden mental state, right? The use of speech and language, accompanied by, things like facial expressions, body language, etc. And, in other, in some cases, even be complemented by physiological or neural measures like ECG or EEG. Right. In addition, you can also get contextual measures, right, with these devices, right, that we carry or in the environment about, the sounds and the temperature in line. So together, right, provides us a contextual sort of, a framing of the kind of speech and spoken interactions or, in general, behavioral and, aspects of humans with which we can, get insights about, what is what regular patterns, is there anything atypical, etc. So to operationalize behavioral machine intelligence, right? So we need foundationally, the nuts and bolts, as I call it, right? Advances in multimodal signal processing, sensing, right? Data from people, from the environment, as we talked about, with which right now we can actually predict constructs that are clinically or scientifically interesting. I'll show you some examples later. You can think about things like, simply, affective state, right? How stressed a particular person is, for example, might be of interest in a given application. But more than that, right, we might also be interested in, the interaction processes and mechanisms, right? How these things change over time, for example, in specific context, right? In the presence of someone, the presence in a particular environment, or etc. So that kind of computation modeling is also possible with these advances that are happening in these in machine learning, especially, with various rich architectures afforded by, the deep learning systems. And of course, we have to translate them into applications. So again, operationalizing, requires all these things in the stack. And so, of course, this is something that's been going on for years, right? So whether it is, deep or involves deep learning or not, right? Significant advances have been happening in all these aspects, in detecting, classifying, and tracking various aspects of, human behavior and interaction, from speech, from spoken language, from language, in other forms, right? Everything from an audio-video processing, automatic speech recognition, computer vision, and of course, lately with these IoT technologies for modeling and sort of environmental modeling, edge processing, many things are going on, right? Significantly, and signal processing, machine learning are key enablers. So that's been an important aspect. Just looking at speech and language, right? Technologies, it's not just one thing, right? As you probably have noted, right? There are many components and that have to be brought together for a given application. Right? Everything from knowing word or speech activity or voice activity to complex models that with attentional sort of layers and so on for jointly processing, say, multimodal information like speech and facial expressions, or speech and body language, and so on. All these things are active areas in research and development with varying degrees of technology maturity. Some of these, as we know, right, like automatic transcription in multiple languages, right? It's now sort of deployed at like global scale by many of these leading sort of industry. Some other areas are still sort of not there yet. Still like areas of research, but there's exciting times for speech and language processing research, and it's sort of impacting the world. So that with which, right, we're able to imagine new sort of domains and applications such as in sort of health and so on. The other thing I want to sort of underscore here is, especially we mentioned that speech carries information about not only sort of words that sort of we're trying to convey our intent, but many other pieces, right? And so one particular perspective in processing speech is the human perspective, right? Not only in our listening and understanding what someone said, but we also sort of have a perspective of sort of tracing what the person's expressed affect is, or who they are, what language they're speaking. So this human perspective, right, which often we use sort of interchangeably with the machine perspective, right? Using human labeling and annotation as a way to guide the machine perception, right? Are sort of two sides of the coin. They are sort of aligned in many problems, but they're also distinct in some ways. So we can think about like processing architectures, right, where we use human perception and judgment as a base for informing algorithms, and algorithms also sort of looking for patterns and informing human judgment. And you can actually together in a collaborative way think about doing sort of building this machine intelligence capability to a level that's sort of better than either think by itself, right? So especially in the health domain, right? So we often rely on, while sort of clinicians, right, look at many pieces of information, data, right? They look at history, they look at sort of assays from the lab, or they look at like radiological results, and then they make their best clinical judgment, right? It's not, we don't know what it's not formulaic, right? The human complex decision making involves all kinds of non-linear processing that we still don't understand how an expert does that. And different experts might have different ways of both arriving at the same result, but arriving at like slightly different opinions, right? And so how do we understand that with the machine learning lens? How can we combine what data science tells us directly? How can we sort of integrate these things and come up with novel ways of looking at diagnostics and treatment planning? So that's a new sort of an exciting area. So to make a lot of these things happen, right, we need data, right? Both for fundamental algorithmic development, in speech, right? That's one of the things that it's been, it's not a new thing, in speech processing has been sort of community has been leading this, right? You may be familiar with the TIMIT database, which is like early days, for speech analysis and speech recognition, to many other things that that have been collected, now around the world in many languages, and have helped propel some of these algorithmic development, in speech and processing and natural language processing and so on, right? And lately, this has been translating into multimodal data sets, audio video data sets, and this kind of shared resources are important, critical for both the research sort of advance, but also helping them be sort of used in practice. So for students, I think especially this data sets. So in summary, behavioral machine intelligence focuses on human-centered ways of computing with human behavioral data. Speech, spoken language is a big part of it, to provide meaningful analysis, hopefully with like collaborative integration of human expertise, which includes their perspective, like annotations, labels, or how they implicitly act in spoken interactions, for example, alongside automated processing. So this is sort of the landscape. So with which I'm going to now jump into some examples. Okay, I think this is a 1.5 hour lecture, right?
Yes.
Okay, so I'll pace myself. I'll talk too fast. So I'm going to take some case studies, from modeling using speech and spoken language, and then use a couple of examples where we can translate them for health diagnostics or in treatment, like in psychotherapy, just to show some examples. Let me pause here and ask if anyone has any questions or anything thus far. Am I speaking? Am I audible or understandable?
Participants, if you have any questions, you can ask.
Or sort of, if people are, if I'm not speaking too fast, or is it okay? The pace is all right?
I think it's okay.
Okay, very good. If there's any sort of difficulty, in hearing me, or if you want me to repeat anything, just interrupt me. It's okay. All right. So the first domain is like sort of, we are all very familiar with, basic speech processing applications, right? Like voice activity detection and speaker recognition, speech recognition. But the same speech signal, right? Can also be used to map into higher level constructs, behavioral constructs that may be of interest to a clinician. And so what I'm going to show in the next few minutes is an example where we can treat this behavioral coding, as we call it, right? That is mapping from behavioral data like speech and spoken language into behavioral codes of interest. To illustrate that, right, I'm going to use this domain of couple therapy. So when people have issues in their relationship, go to a counselor or a psychologist or who sort of looks at and listens to people, the couple interacting, and they try to map it into useful behavioral constructs with which to understand how the affective dynamics are, playing patterns, and so on, or interests or behaviors of interest, and then they can understand what some of the challenges are, and then they can guide the couple for with their relationship sort of problems. Right? So many of these psychological sort of research and practice domains, right, codify the behaviors of interest by sort of in a very well-defined, theoretically often sort of grounded behavioral codes or constructs. For example, in relationships, right, they each of this is corresponds to a rating system. For example, in one particular behavioral coding system, right, say social support interaction rating system or couples interaction rating system, right, or examples. Some of the codes that are analyzed, right, are things like, what is the level of acceptance the spouse is showing toward a person is showing toward their spouse. What is the level of blame, right, and a scale of 1 to 9. So you can think about it. There is a construct like acceptance, level of acceptance. There's a definition for it, right? It's a linguistic definition saying, it says it indicates understanding, acceptance of views, feelings, etc. And so a human is trained to sort of internalize this construct. This construct here is acceptance, and they listen to someone interacting and watch them interacting, and then they try to map, sort of using their mental model, the presence of this sort of construct maybe in a scale of 1 to 9, right? Likewise, level of sadness, use of humor. So for this domain, these are some of the higher level constructs of interest. How are they signaled? Through speech, spoken language, through sort of visual cues, and these are codified. And this is just an example of one domain, right? Interaction, in couples. But this type of, an approach is very common across behavioral mental health. So one of our first things, years ago, right, we did we said, well, we had videos of about 100 hours in those days. It was a lot of data from our colleagues, and we said, can we try to automatically use speech processing to get at these behavioral codes directly, just like a human rater or observer would do. So that was the problem formulation. Very simple number. Right? So we had data from a lot of people.
You work too much.
So I want to talk about
who were, complaining about couples interacting about their issues, and so we had data about it. And here's some an example transcript, right? So they're supposed to discuss some problems and freely, and you have this kind of interaction. So immediately can the speech processing people in the audience can imagine, right? We have audio. We can diarize it and assign turns to each speaker, identify who they are, what are they speaking about, and then try to see whether we can use this data for processing the kinds of constructs we're interested in, right? So that's exactly what we try to do in a very simplistic way, right? So we had data about all these constructs like acceptance, blame, positive, negative affect, etc., right? For both coded by experts for both the husband and wife. These were heterosexual couples in this particular study, and so we wanted to see if we just use sort of, just audio data, right? Just the vocal speech features, how much can we kind of estimate these constructs, right? So we put together a simple-minded system in those days, right? It was a long time ago, 10 or 12 years ago, right? Already outdated. So we sort of did the usual pre-processing of the audio, got rid of, bad audio data. This was sort of far field data, did speaker diarization, and once we had speaker homogeneous segments, we estimated a lot of low-level descriptors, features that one could get directly from speech, spectral features, voice quality features, etc., etc. You can also run an ASR and get the lattice, and from which we can get best list, for example. And then you can use these speech features and or language features in some of our sort of favorite machine learning, algorithms, since it was just a binary detection, right? High or low level of these presence of a particular construct, like blame or sadness. So we just used simple logistic regression, or SVM, right, for early experiments in 2009. Right? So what was very exciting and encouraging is that we got like accuracies, that were comparable to the sort of annotator expert agreement. So it was much better than chance. And so it was very encouraging that even just simple speech features like prosodic and spectral features had very useful information in informing us about these complex behavioral codes, right, from the entire session. So with this sort of encouragement of initial results, right, we started building this behavioral coding from rich speech data, not only vocal features, but also say, now what happens if we take the noisy transcripts from the ASR? That's the language that provide us information about these behavioral states. Of course, there's lots of excellent literature in psychological sciences about that, right? The use of, for example, specific patterns of pronouns, right? The use of first-person pronouns versus second-person pronouns, right? Are supposed to have specific behavioral meaning. For example, a high blame utterance, right, always has second-person pronouns, and the language models which we use right here automatically sort of caught these kinds of observations that people have made, right, in a data-driven way very easily. So of course we can combine, acoustic and language information and improve performance of these behavioral coding, progressively, right? The more pieces of information we add, like it's helpful. Something that's so with this, right, like very basic sort of work, we kind of one could now think about more complex ways of understanding and modeling sort of these human communication and interaction behaviors, and try to see when these things are disrupted and try to make it clinically meaningful. A lot of different things, right? Simple, classification and it's not enough, right? So one of the things that it's interesting, human behavior is like multimodal, sort of expressed and processed, and it sort of varies according to context. How do we kind of combine context-sensitive learning with multimodal approaches? So one of the early work we did was to use these bidirectional LSTMs in this affect modeling, and was like one of I think first papers in this domain. And so these kinds of problems actually inspired us to create these novel sort of machine learning, deep learning architectures. The other is like when you listen to a whole 25-40 minute session, and we want to come up with a summative or global codes, right? How positive was this interaction? How positive was this this particular person in this interaction, or how sad was this other person in the interaction, right? We want to know how we can pick or pay attention to specific, in current day lingo, right? Attention-based models, right? To specific portions of the interaction that best inform this overall judgment we are constantly after. In the early days, we kind of post this sort of multiple instance learning formulation with diverse density SVMs, and later on, these have been extended to more current architectures. other kinds of computation models that are not easily sort of observable or codable by just listening or models of synchrony or training. So, for example, it's known that when there's positive dynamics, right, people's behaviors tend to sort of synchronize or coordinate. Like, for example, people's prosody or use of language or even nonverbal behavior, like head motion, tend to sort of synchronize. So the question is, like, can we automatically recognize and model these kinds of entrainment behavior and try to use this to understand the nature of the interaction? So these are just some examples of the questions that we possible and we try to answer. So, for example, like just the early sort of formulation of this multiple instance learning, you can think about like in a long session with multi-turn, right, dialogue, right? We want to know which of these turns are most informative about an overall judgment that a person, an expert would have given. For example, about the level of acceptance or level of blame, or so on. Right? So, in this formulation with diverse density SVMs, right, to detect the salience prototypes, right, we had this idea of positive bags and negative bags. Yeah, and so instances close to positive bags are far away from negative bags, right? You can imagine current day formulation, you can do this with triplet embedding, right? Like, positive anchor, sort of anchor positive and negative examples, and you can declare as a salient prototype those such instances. And so when you have new data coming in, right, you can compare with this sort of salient prototype, and it's almost like sort of compression or coding, right? And then use those to for classifying specific sort of states of interest or constructs of interest, right? And so we showed that this kind of saliency detection through multiple instance learning actually provided not only sort of insights into what turns or interpretable sort of information of data that informed the decision, but also sort of improved the performance. It kind of, since it cleaned up or filtered the data nicely, we showed we got like good robustness. So very interesting sort of result. Of course, what will we apply for audio, for text? Also sort of extended to visual behaviors like head motion and so on. And this is sort of one interesting sort of application of machine learning to understanding complex sort of behavior, at sort of a global level. The other example I wanted to sort of highlight is this entrainment. That is, for example, you can see, ask how much do two people synchronize in a conversation, right? Like, for example, if two friends meet after a long time, they start sounding alike, right? They laugh together, they move their head together, and so on. Now, can we put our finger and quantify this measure of entrainment behavior that's going on? So in early formulation, what we did was, look at, for example, prosodic entrainment. So with the vocal features that we can extract from speech from both sides of the interaction, we can embed them into sort of some sort of a space, like PCA type space. And once you have these distributions in space, right, you can then compute similarity metrics, right? Like there's so in L2 type of metric or other kinds of divergence measures that we can use as proxies for entrainment in this behavioral space. So how do we evaluate the goodness of this? Right? You can say, we can then look at scientific hypotheses. If people are supposed to be entrained, right, then like the interaction mechanism is supposed to be, for example, have more positive affect. So we can try to see if these features are good or improve performance for affect prediction, for example. Or when you scramble this information and show that it should behave in the opposite way. So a lot of very interesting ways of using computational measures like of entrainment to understand sort of coordination and synchronization and interaction. More recently, so there's a paper that came out in 2020 in the transactions of affective computing, is to have a more deep learning formulation for the same behavior, that is looking at similarity in behavioral interaction. Of course, as you may have heard through this short sort of this course, that we can now represent acoustic features with these that we model with deep architectures, right? Like one of the layers just before output, we can treat that penultimate layer, for example, as a representation. We call it embeddings, and then we can do operations on this embedding to look at similarity or other transformation. For example, in this particular work, we computed entrainment sort of as distance in this embedding space. Right? Of course, empirically, a number of different modeling approaches were tried. Especially the one that was very promising was based on sort of the I vector based embedding distance. And what very exciting was to see how these entrainment measures were able to sort of predict things where the presence or absence of synchrony was implicated, right? When there's a lot of entrainment, in cases like agreement, or less entrainment and blame behavior. Also, in fact, they were very powerful in predicting outcome of couples therapy, which we'll talk about in a moment. That is, did this relationship stay the same or improve or decline, right? Etc. So this is sort of how we formulated this I vector-based triplet network entrainment distance, and ITNet, that we call. And the idea is very simple. Is that triplet embedding, right? We have an anchor, and we compare the positive negative example, and the idea is that the negative example was strategically chosen sort of from some other turn, right? It's not a consecutive turn, so we expect that to be not that similar to two turns, right, of speakers that are consecutive turns that we're comparing whether they are synchronizing or not, right? We expect local turns to be more aligned, right, if they're entrained, than compared to some other random turn from elsewhere. Right? And so in the training, we minimize this triplet loss, right? That minimizing the positive distance and maximizing the anchor negative distance. And so this was found to be a very powerful model as sort of the entrainment distance and in predicting all the kinds of things I talked about. So of course, this kind of entrainment, again, can work beyond just speech vocal data. We have applied this to sort of audio-visual data, movements of the face, head, hand, and so on. But the methodological aspects of bringing these machine learning methods to understand both these constructs and the mechanisms is sort of very common across these sort of places. So now with all this stuff, right, what kind of insights can we get, right? So one of the experiments we did, like, this data, as I said, right, comes from a clinical trial. And so couples were followed for 5 years, and we had some statistics on what happened to them at the end of this 5 years. Did their relationship improve, or does it go, that stay the same, or did not improve? And so we were going to see if data that we had of them interacting earlier, year 2 and so on, could it actually predict the outcome, supposed to make retrospectively. And so we had about sort of 100 or so sort of couples, like, we have sort of the distribution of the number of people whose relationship declined, or there was no change, or partial recovery, or full recovery is there. So we had 2 sort of observations of these people over at 26 weeks and then or 2 years, right? We have the couples interacting, and so we wanted to see if the data from these interactions tell us something about what would have happened, at the end of 5 years. It's just a thought experiment. So the features that are very familiar to speech researchers, right? Everything in kitchen sink that we can get just from the speech data, spectral features, prosodic features, and voice quality features, and we computed them, for both the husband and wife data separately for all the sessions, right? 4 interactions from both sessions. We also sort of looked at the data with relation to themselves, the dynamics of how things change, these vocal features of the same person in the session, and also with respect to their partner, the relative changes. So we also had experts code these interactions, right, using the standard operating procedures that they have, the behavioral codes, right? We saw that like if you use the expert-derived codes as your features in the classification, right, to predict the outcome, right? The behavioral codes sort of capture about with accuracy about 75%. It's pretty good, much better than chance. But if you just take static functionals of these acoustic features, they did as well, which is pretty exciting, right? Now, if we kind of introduce sort of the dynamic features with like both within a person and across these couples, right? We got like much improved results, like statistically significant improvement. And if you use both static and dynamic acoustics, right, it did much better than what human behavioral codes could provide. But now, if we combine both the human data and the acoustic data, right, it still sort of performs the best. So it's good that there's complementary information, that humans are catching something that the machine is not, and machine is catching something that humans are not, but together they do better. So that's an example. So we could get sort of outcomes, about 79.6, which is pretty exciting, that we can predict things like that. But that was retrospective, right? That we had data and we looked back. So in one study, what one of our former lab members did, Professor Federico Gaspari and her colleague, Professor Adi Timmons, were both of them students before they became professors with us. So they kind of said, well, can we do such behavioral predictions prospectively, that is, before they happen? For example, detecting conflict, right? Say in couples. Right? So they had a complex, like multimodal wearable system that recorded audio when the couples were in proximity, recorded biosignals, ECG movement. They also got like momentary assessments from them about how their day was going and all that stuff. And with which, of course, they also had information, baseline information about whether a conflict happened or not. And they used this for sort of, automatically figuring out the conflict detection. So that was pretty exciting, and I'll show that later. So another sort of clinical example with speech, right, and sort of machine learning is a recent paper that we did in a sort of more longitudinal way. That is, can we track changes in clinical state, right? Mental health is not something that is, a static aspect, right? How the state changes, especially in conditions like major depressive disorders and so on, right? Are the mechanisms of change are not well understood. So if we are able to use speech and spoken interactions as a way to mark and predict, ahead of time state changes, then we can intervene and provide the right support. That's the motivation. And so, of course, major mental illness needs are tremendous. The U.S. statistics show that over 23 million people, many, 1 in 5 people live with mental illness, but only few people get treatment. Right? So the idea is, like, how can we provide scale in the speech and language and information? One sort of avenue to gather information, help provide support, right? Understanding underlying neuropsychiatric states. So that was the motivation. So here in this study, we tracked about 47 participants over a long period of time, about 4 to 14 months. They called sort of, every week answered some simple questions about, how the day was, what was good, what was not good. And experts, clinicians, assess them as they would at their mental health state. We also then, analyze their speech, right, acoustic features, lexical features, etc., and try to see if we can predict the provided ratings and changes. So we found that there's a lot of useful information, right, the prediction of negative emotional words and negatively correlated with with the providing ratings and use of complex language and readability. They're all useful features that help sort of predict expert ratings automatically, of course, in cross-validity. So again, sort of underscoring that the presence of useful information that's available in speech and language, even remotely, sort of on a phone, won't collect. That may not be present otherwise, right? Because unless a doctor or sees a patient or someone, detects, right, when it's too late, right? That might be more dangerous than if we're able to predict this early on. So that's kind of the motivation to use these kinds of. So this is the example that I was talking about this predicting conflict, one step ahead in a multimodal sense, not just with speech, but we can complement that with other kinds of information like electrodermal activity, ECG, and so on. With the current day variables and things that are happening there, the promise is again very high. So we are able to piece together these multimodal streams of information, use it in a deep learner, right? And then, of course, we can get good classification accuracy with these multimodal information. That's even better than what one could glean from what people themselves said about their how their day was with respect to the conflict that they had. So again, this is very exciting, and this is in fact gone on to be some patented technology and spin-off and so on. So I would just quickly mention that this kind of, again, using speech, audio information in conjunction with other forms of information about the person, egocentric way in context, right? Is now is opening up a lot of new possibilities in understanding sort of, people's behavior, health state, and its changes in real world context, right? Like in not just, in clinical sort of conditions, but also in day-to-day, how we manage stress and how it impacts our productivity or health, like sleep and etc. So in one study, right, we collected data from healthcare providers, like nurses and doctors and so on, for 3 months continuously. We recorded, with an audio badge, a voice for every day for 3 months as they were working in 12-hour shifts. Physiological data, movement data from like Fitbit-like devices, their digital activity on the phone. They also answered survey questions every day. So tremendous amount of data from about 400 people, and we have released the first data set from about 250 people, in Nature Scientific Data. And so this has audio, of course, not labeled, right? Because these are egocentric audio alongside physiological data. Now we can imagine how we can bring things like deep learning to understand patterns and changes and in day-to-day behavior within people, across people, etc. So speech and context, right? Type of studies in real-world situations now is possible. Again, I would like to underscore this converging sort of sensing, processing, machine learning, all working together. So, for example, this is a snapshot of a day's worth of data in one subject, right? We have sleep data that we have from the wristband sensors. We have movement data when they're sleeping. Of course, they're not moving. So when we see step data when they're awake, heart rate data, audio when they're talking at work, and when they're talking, where they are, and their survey answers when it was provided. Very rich data set. Again, for those who are interested, this can open up a lot of very interesting deep learning based approaches to gain insights into human behavior, right? So, but speech is our core, right? With which we found a lot of very interesting sort of patterns, right? Sleep patterns between day shift, night shift workers, how much they talk, their sort of heart rate variability, right? The rhythm that they have, etc. Or not. So, for example, we found that the biorhythms of people for night shift, right? The cardiac rhythm was more variable in night shift workers than in day shift workers, which has had a particular daily heart rate patterns. So in summary, right, such data, right, speech-centric machine intelligence in context of other forms of data offers even richer ways to use these deep learning approaches to build interesting models about human behavior interaction to turn predictions. So lots of curves. I'll share the slides. The next two examples are shorter. I'll just touch upon sort of multimodal approaches in this another domain from a diagnostic perspective. I'll sort of highlight some possibilities in autism spectrum disorder. So autism spectrum disorder, as we mentioned earlier, is a developmental disorder, meaning arises like early in life. It's neurogenetic in its sort of origins, but it's better understood in terms of the communication and social interaction patterns in individuals. And so places where sort of technology, the kinds of things we're talking about, machine intelligence, can be of help is to better understand these patterns, to stratify behavior with quantifiable metrics, and to track and quantify, for example, changes in the context of sort of treatment or interventions. So in ASD, autism spectrum disorder, right? To care, it's also a spectrum disorder, meaning different symptomologies along these dimensions of social communication exist, right? Mostly along sort of language and interaction, stereotype behaviors, and every individual sort of displays or manifests it slightly differently. So to characterize, right, people look at all these various dimensions and so try to understand. So amongst the many things, right, like just to illustrate where speech processing can come in handy is looking at the prosodic aspects, like how the music type in speech. Let's dig deeper. So a clinician, when they use one of the very well-known sort of diagnostic sort of observation sort of instrument called ADOS, Autism Diagnostic Observation Studio, right? It kind of describes qualitatively atypical prosody as something that's slow, rapid, or jerky, and irregular rhythm, odd intonation, and so on. Right? Very qualitatively described. A trained clinician is able to take this description and map it to on a scale of say 0 to 4, sort of marking the presence or absence of atypical prosody on the scale. Right? So what can complement this? Right? We thought would be using speech processing and machine learning to see how we can take markers corresponding to these prosodic variables and try to quantify differences, across individuals, right? In here. So we know that intonation, volume, speaking rate, voice quality features are all like some of these speech signal analysis sort of it's constructs that we can get from speech to describe various aspects of the suprasegmental properties of speech, what we broadly call prosody. So in this sort of early experiments, we kind of use features derived from pitch and intensity and speech rate, etc. So one of the early results, which was what was qualitatively sort of described as monotonic or abnormal volume, etc. Right? We showed that in fact these the Spearman correlation between the rated severity and these prosodic cues that kind of try to capture these various properties of monotonic speech, abnormal volume, were statistically sort of highly correlated. Confirms the qualitative sort of descriptors, sort of and we can kind of find the quantitative sort of proxies to that, right, from directly measurable functions. That's encouraging. But what was also very exciting in the study was because this data came from interaction between a child and a clinician, we also analyzed the prosodic properties of the interacting psychologist. And we found that, right, there was a very interesting correlation pattern between the severity of the child that the psychologist rated and their prosodic patterns. That is, that they changed their vocal prosody depending on the severity of the patient, right? Knowing that and showing that the psychologists also have very useful signal because they're changing their engagement strategy or spoken interaction strategy, some of it is sort of, understandable why they're doing, like, for example, asking a question more, but some of it, like changing voice quality to match perhaps the voice quality of the person they're interacting with, is more sort of, a characteristic of a human interaction or affinity for finding than something that is, clinically sort of, that they're trying to do. So in fact, we found that we use the speech features from the psychologist, we can use that to predict the severity of the child that they rate. So showing that, we have useful signals on both sides of the interaction, and machine learning can be helpful here to understand. So that was an interesting sort of observation. That is, these kinds of tools can allow us to complement what the psychologist observes and marks by modeling the whole interaction, right? This provides another perspective. Of course, what we did for prosody can be extended to understanding language use, turn-taking patterns, how much speech, how much silence, how much overlap in interaction, speaking rate, all these can be computed. And in fact, here are some results we found that sort of when the trends with severity, right, the amount of the speech that the psychologist had increased when there was a decrease in speech with severity for child, indicating the psychologist is working sort of harder to engage the child to speak more when they speak, the child spoke less. Likewise, when there was increased latency when the child was speaking with their higher, which was correlated with higher severity, clinical severity, the psychologists also sort of increased their weighting, their latency to sort of be more sort of in tune with the child's sort of interaction patterns. So this also sort of similar patterns we saw in the language use. For example, the use of personal pronouns decreased in the children with increasing severity, and the psychologist was trying to adapt to compensate for by using more personal pronouns to encourage perhaps to engage the child more. Also, it's true for nonverbal cues like sort of use of fillers like right? With the severity, the child used less fillers, right? Because they are sort of indicating that the planning process was different, and we saw that the psychologist, the interacting psychologist, also sort of reflected some of these in decreased use of non-fluencies, right? More clear speech and so on. So very interesting patterns by doing this kind of speech-based, machine learning-based models. Of course, this kind of work, is happening lots more with the increasing amount of data, with more sophisticated models. But so the use of speech analysis, speech-centric machine learning is a very useful, important tool for in domains like clinical domains like autism, for characterizing interaction, supporting clinical understanding and and clinical sort of, applications. Of course, whatever we do with speech, similar approaches can be used with visual sort of behavior as well. Here, for example, right, just like prosody, production of prosody is deemed atypical, and its perception also has been characterized clinically as awkward or unusual, right, by a listener, and that became a sort of a barrier for interaction, particularly with children, right? If someone sounds different from themselves, right? It affects relationship, friendship building, and so on. Same thing with facial expressions, right? Even though a child with autism may smile, it was often deemed to be awkward or unusual. Right? So we want to understand what is the mechanisms underlying this kind of differences in a child with autism and the perception of their social cues, both the production and perception. So we studied expressive facial and vocal expressions. So one of the results, just cutting to the chase, we found that by using these computation models, that there's reduced complexity in the facial behavior, especially in regions far away from the mouth, like eyes and so on. But in this, one interesting study just highlight here, which came out like a couple years ago, is the dynamic relation between vocal production and facial expression, right? Especially, we wanted to know how cross-modal coordination works, that is between vocal and facial expression, especially in a social context. So the results, we use Granger causality analysis, modeling these vocal and facial dynamics, right? And the results showed that neurotypical children, that is, children not with an ASD diagnosis, produce sort of expressive sentences, right, with strong cross-modal coordination, that is between prosody, vocal prosody, and facial expressions. When they sort of spoke neutral, like sentences with neutral affect, right, the cross-modal coordination was weaker. So they used differential expressions of coordination when they were trying to be more expressive. The second observation we made was that in contrast, ASD children did not show any differentiation in this cross-modal coordination between expressive and non-expressive sentences. In fact, one other interesting thing was that when the non-ASD child was in a social context, right, then the cross-modal coordination was much more sort of increased. That is, they spent looking more at a face when they're interacting. But when an ASD child, right, was in a social context looking at a face, right, this cross-modal coordination further weakened. So that this shows that the mechanisms of face-voice coordination is different and distinct, right? It's affected in children with ASD, and it's also sort of context sensitive. That is, depends on the social context. So we can get our fingers on that through sort of these data scientific approaches using computational modeling. And so this is an example of that. So the final sort of use case I want to close this lecture with is from sort of the treatment domain, like psychotherapy, which we mentioned. There are different types of psychotherapy that are popular. We've heard about cognitive behavioral therapy, motivational interviewing, etc. So one of the things that we are interested in is in characterizing the quality of psychotherapy. So from speech and language, right? Because these are conversation based. So the question we're asking is, can you use sort of speech-based machine learning to provide insights about these complex sort of interactions that are going on in psychotherapy, right? So, one of the important measures, right, is the empathy that's expressed by the therapist in a session. It's supposed to be a good marker of a good quality therapy, right? So how do people express empathy that is, perceivable by the patient is from what they say and how they say things, right? So we examine if speech prosody measures, right, provide us information about perceived prosody, perceived empathy of by the therapist. So of course we had humans rate, observers rate the empathy that they felt expressed by the therapist as the reference, and we try to see how the speech features sort of across these various empathy sort of conditions vary. Right? So we found that lower perceived empathy of therapists when generally when there's like high energy in their speech or higher pitch values, etc. So kind of showing that there's some signal in in how therapist empathy is perceived. Now, of course, we can put this together in a machine learning system to see if it can catch. So we built this sound to code system, as we call, going from a recording in a clinic, a conversation that's happening during a counseling session, using the whole pipeline, right? Voice activity detection, variation, speech record, and then build a machine learning model to do this empathy estimation, right? We found that in fact, by using this kind of a pipeline, we could approach human agreement about empathy rating. In fact, this is now the system is used in many mental health clinics in the US. So of course, from that simple system, we have gone on to use more complex deep learning, multi-level, multitask formulation to evaluate across different psychotherapy approaches, and are and making this more scalable and broadly applicable. Yeah. So in summary, right, using all these examples, what I tried to sort of convey here, that these machine intelligence, speech-centric, human-oriented, multimodal machine intelligence approaches, right, help provide like two sort of things, right? One, where there's sort of missing information, sort of these machine intelligence approaches can help, fill the gaps of human knowledge, right, by looking for patterns in sort of the vocal properties, or how vocal properties of two people, like synchronize, or what's the relation between, say, speech features and facial features, etc. Right, where there's gaps in our knowledge that can help them. It can also help connect dots, between things that we are not that obvious. So a lot of opportunities, right, across this ecosystem, and from getting the right data, doing sensing in natural settings. Right now, speech is sort of so ubiquitous, right? You can get to the person in their real world setting, so we can capture speech, but we have to do that in a very not just from just a technological point of view, but also in respecting privacy, ensuring trust and integrity, depending on sensitivity. A lot of different layers to this. Right? So that itself is a very interesting, exciting problem. Once you get the data, right, what do you do with it is also an exciting question, especially if you want to derive information about very hidden, complex states like affect or mental health state, etc. And how do we make it interpretable? How do we derive these interpretable features and rare events, right? Anomaly detection. All these are very interesting machine learning questions, right? And current deep learning formulations may not be directly applicable, and so a lot of opportunities exist. So in summary, right, human-centered machine intelligence is a framework where that aims to support human and/or autonomous decision making and action using this sort of integrated view of sensing, data sciences, and AI, help us do things that we know how to do, but do it more sort of consistently. Create tools for gaining new insights and tools for discovery, thinking about how we regulate, for example, affect, right, day to day. And of course, translate these into useful diagnostic and interaction tools, with which I will conclude my lecture and thank all my colleagues whose work I kind of used and presented together.
So thank you, sir. It was really a wonderful presentation, and I hope that participants have learned about introducing machine intelligence using different psychological multimodal data. So we can take some couple of questions from participants. So participants, if you have any questions, you can please ask. Maybe you can unmute your mic and ask. We can take a couple of questions.
Hello.
Yes.
Thank you, sir, for this wonderful talk. So my question is like, so you mentioned about speech production and facial expressions, right? So can you please elaborate more on cross-modal coordination? Like, how are you doing this? Like, how are you like interpreting this facial expression and then drawing some analysis from that? So.
Right, that's a good question, right? So for example, right, we can, once we have these observations, in this case, right, we had video, but also in some data we had actually 3D motion capture of various parts of the face, right? From video, you can use various ways of quantifying moving images, either directly pixel driven or different regions, or others may use the action unit sort of parameterization. So We just use basically different facial regions with these movement data. So as time series, so you can think about facial movement over time when people were speaking as sort of set of time series. Synchronized with it is also when the speech data, right? Like various features you can extract from the speech audio, right? Spectral features, computed at whatever time. You can also, in fact, derive other kinds of voice source features. So what we have is essentially we can think about various ways of these multimodal time series. Now, then we can look at sort of how to analyze and model them jointly, right? So that's exactly what we did when we were trying to use coordination between sort of we use sort of fit dynamical systems model, right? We were looking for a range of causality patterns. If X causes Y, you can look at the reference, but simply, we can try to see some measures of how these streams of data are coordinated, or that is meaning is a predictability of one from the other, or how much information, you can do simply, in many ways, right? Including computing mutual information or other kinds of metrics. So a number of modeling ways. So an important point here is that once we have these rich cross-modal data streams, that we can try to find the information across these streams, how one can predict the other with various temporal lags and so on. So to gain insights about these mechanisms, how two data streams are related. And here, since it's related to sort of visible articulation of the face, right? Related expression and the corresponding vocal processing. Here, we're especially interested in expressing aspects and so how they were not related.
I'm sorry. So basically, you are trying to coordinate like facial, like image, like getting the video for the facial expression, and speech, like audio from, audio. And right. Then trying to coordinate these two signals.
Right. So of course, we use certain methodology, and of course, people might come at it, these questions from other methodologies, like So I direct you to a paper by Tanner Sorensen et al. In Nature Scientific Reports in 2019. You can get some insights, and a number of other papers also from our lab, various aspects of these multimodal or cross-modal coordination.
How about using only speech signals? Can we do that, like for these images, videos is also necessary?
Yeah, for what would you like to do with the speech signal, right? Like you can, of course, extract a lot of very useful information from speech, right? For example, the study on prosody that we talked about was just from speech. In fact, was just from the vocal audio, not even the text, right? So we can add like different pieces of information together depending on the questions we're trying to ask. So that's what is very fascinating about when I talk about speech-centric machine intelligence, right? Speech is so rich, it has multiple layers of information. Just from the audio, it has, the voice source information, articulation information. Then the language, corresponding to the speech, the nonverbal sort of cueing that we provide by, our hesitations, our pauses, our, laughters and all this stuff, right? Everything is very, richly informative about, how and what we are trying to communicate, our state and our traits and so on.
Yeah,
just audio also is very useful, and in some cases you might only get audio.
Mm-hmm. Okay, thank you, sir.
So, any other participants?
Sir, I have a question. Hello.
Yeah.
Yeah, sir, I have a question from the speech-based emotion recognition area. So I started learning from this emotion recognition from your lab papers, and I found that there is 3 scopes are there, like no model have all 3 features together, like gender independent, speaker independent, and language independent. So, sir, I did the experiment from the publicly available data sets like Savvy, Ravdis, EmoDB. And when I am taking each feature separately, I am able to get the desired result. But when I'm trying to trying to achieving all three features, means my single model will be gender independent and speaker independent as well as the language independent. So I'm not able to do it. Would you please provide some input?
Yeah, that's a very good question. The question is about, I think, Shivam, right? Like you
Yes,
asked.
sir.
Yeah, very good question, Shivam. So, question is about, you know, uh, how can you make, the performance of, say, express emotion recognition, right? Sort of independent of other potential dimensions of variability. So what makes speech fascinating and rich, right, is the information it carries about multiple pieces of information about not only, our internal state in some ways, but who we are, the language we speak, and our age. All that kind of is wrapped in the signal, is one-dimensional signal that we produce. So when we try to marginalize the effect of other variations and generalize sort of across people, we find that the amount of information that we are able to successfully take that can inform us about specific sort of say in this case emotional state while suppressing other pieces of information becomes sort of more challenging because we are getting rid of things that may be inherently informative about uh, how a particular individual expresses emotion. And that contains, so individualized models and so on are very important, because everyone has, while there are commonalities of how these signals are used to explain emotions, but there's also sort of dependencies that are important. So people have been trying to do this as sort of these multitask, multi-labeled sort of problem, formulation instead of marginalizing. But some of the challenges there are amount of data that's needed to capture the range of expressive variability, for example, depending based on say emotions that they're trying to convey, right? And so this is a challenging problem, right? That because these are intertwined and we don't know how the cross dependencies are, and it's people have been trying novel approaches like in the deep learning sense, like disentanglement and etc. The same thing that what I-vector type thing approaches try to do to move channel effects, right? So while there have been some successful approaches, but I think personally I feel that with more sort of information data and to understand the richness of these expressions, we will get more insights. It's still, hence, if you are just after numbers to make emotion recognition work well on these databases, right? I think personally, models that like your experiments indicate seem. So the question is what is it that we are trying to do? Right? And that's the question I have to ask. Are you trying to build generalized models for emotions across, or join models for all these things, etc. So it's a bunch of open questions, and the specific modeling approaches, in my view, that we adopt depends on the question we're trying to ask. While we're still facing some data limitations yet still to fully answer or explore these questions. There's some nice databases that are emerging with more data, but still I feel that they may not be sufficient for some of these questions.
I have one question myself.
Sure.
So suppose you're using multimodal data. So
Yeah.
all the multimodal data, for example, speech, audio, and visual data. So they're recorded with different sensing modalities. They might be having different sampling rate. There might be some delay also. So how do you synchronize when you feed into a model? And you are also fusing actually the human expertise in that.
That's right. That's right. So that's actually a very, very good question, because each of these data streams are coming at different rates with different reliability, with and and it's the whole notion of synchrony itself is just sort of kind of, even though we may have common time points, right? How they occur, what occurs, and so how do we learn concordance across these modalities, right? It's that's why some of these nonlinear mapping architectures, right, are attractive. Right? they kind of can consume and integrate this information at these different rates. They don't require the traditional, moment-to-moment synchrony, which we kind of try to do typically, right, with up or down sampling and do sample line. May not be needed for some of these classification regression modeling forms, but if we're trying to do synthesis, right, or depending on that, we might have to do some rate adjustments. But in general, some of the methodologies that we are developing or architectures try to handle this kind of heterogeneity in how these data are sent. And that's going to be actually one of the features of these systems, right? That you're not going to be sampling all the sensors at the same rate, not only because they may not provide interesting information at the same rate, but also for saving energy, for privacy, and other kinds of constraints that may come into play. So how do we deal with these multi-rate, multimodal streams to still gain interesting insights? It's again, right now, mostly empirically done, but getting a good theoretical understanding of this for characterizing specific, speech-based human behaviors. And it's still an open research question.
Thank you, sir. It was really a knowledge-generating session. Thank you for giving us time for this session as well. So now I would like to request all the participants to turn on their videos so we can take a screenshot before ending the session. Yes. So you can unshare it if you want and share. Not a problem.
Oh, by sharing screen?
Yeah, you can unshare. Yeah.
Okay, let me stop sharing.
Yeah, I think it's enough. So thank you very much, sir, for giving this talk. So thank you. So so here our session ends. So we'll meet at 12 for the next session. Thank you all. Thank you, sir.
Bye bye everyone.
Bye bye, sir.
Take care.